Welcome back to the video lecture series for Introduction to the Art of Programming using Scala. In this video we continue talking about our spatial data structures, and we're going to start implementing our KD tree. So we saw in the last video how the KD tree partitions space along one dimension, and we can make it so that it partitions at the median, and that way we wind up always having a perfectly balanced tree. And this is a significant advantage over the quad tree, because we're guaranteed that all of our searches, assuming that they don't branch too highly, are always going to be order log n for the search. So we want to look at the code for this. First thing I need to point out is that in the video on quad trees, when I did go to test the code, I found out there was one error. The declaration for max points had been down low in this code. It had been after the make tree, and that's a problem because the max points gets used here, but the initialization of variables happens in order. So if when this occurred down at the bottom, it was not happening until after the call to make tree, so it wound up being 0, which doesn't work very well with our code. So I moved it up to the top, and indeed constants in a class generally should appear at the top with their declarations. So now we want to create our KD tree. We'll make a new Scala class. Let's see, go with the lowercase t. And I am going to start off by copying code from the brute force. And the reason for that is we actually do need a number of dimensions here, whereas we didn't need that for the quad tree or the grid because they were stuck with 2 all the time. But here we have, for the KD tree, we're going to allow it to work at arbitrary numbers of dimensions. I'm going to go ahead and copy code from the quad tree just so that we can start playing with things that way. Let's make this underscore. Okay. So the KD tree, turns out we don't actually need to find the bounds here. This is another potential advantage of a KD tree. One thing that I didn't point out about a quad tree, and this is fairly significant, is if you actually have more than 3 data points that are on the exact same location, or whatever max points is, if they're at the exact location, the same thing is going to happen with our KD tree. This winds up doing an infinite recursion because no matter how small it makes the boxes, they all wind up being in the same place. That generally isn't much of a problem. You generally don't have multiple data points that are in the same location. However, if you mess something up with a quad tree and data points start going outside of your bounds, okay, in particular if they go up in the corner here, every data point that's up in this corner winds up being put in this node, and then the subchild that's up here with the subchild that's up here with the child that's up here with the child that's up here. And so this winds up breaking down nearly infinitely, well actually infinitely, if you put more points out beyond this corner than whatever your max points is. You're going to have an infinite recursion which is going to consume all of your memory. So and that's caused by the fact that it has bounds. Now we made our bounds the minimum and maximum when we created the data, so you can't have that happen. But if somehow the values get modified and you aren't careful about things, that is a possible problem with the quad tree. With the KD tree, you can see these lines that go out. If they touch the edge going straight, they go out forever. This is a partition of infinite space. We only care about the areas where we actually have data in them, but all of these lines down here, they go off to infinity. So there are no bounds that we need to know about there. That doesn't mean that we're not going to need that code, and in fact I will paste it down in the make tree for a bit. So what does make tree take here? Well, it definitely needs the points. And in this case, I think it needs to take the points. I don't really have any additional information that I have to pass through on the KD tree. So that simplifies our call up here because everything else that we had was related to the bounds. Our node for the KD tree does not keep a center x, a center y, and a size. It keeps a dimension that it is splitting across, then a value that it is splitting across, and then it needs two children. So I don't necessarily have to do this as an array. I could just do this as left and right. In fact, I will go with that approach. Left is a node. It starts off as null. And then the same is true for right. And then we do need data points in here. Okay, if we realize that I've forgotten something, we'll come back and add it in just a bit. So each of our nodes has what dimension it's splitting in. For our picture, this would be either x or y, but it could go up to arbitrary numbers of dimensions. The value that we're splitting on, oh wait, the dimension is not a double, it's an int. We're not going to allow you to split on dimension 2.73. So 0, 1, 2, 0 for x, 1 for y, and then etc. Okay. Visit neighbors we will come back to. I'm going to go ahead and comment that out for now. And then the make tree. Okay, this is where we want to start working. So what happens with the make tree? Well, first off, we have to pick what dimension we're going to split along. And the way that we pick what dimension we're going to split along is, actually let me cut that and paste it down here, okay, is by finding out the bounds. Okay, I want my min and my max values. We'll come back to that though. Obviously our base case is there aren't, the base case is that there are few enough points that we don't need to do anything, in which case this doesn't split at all, and I can pass in things like 0, 0, and that's it. For my node, those are currently vals, which means that this is going to be problematic. So I'm going to move the declarations into here. Val in is a new node of 0, 0. In this value of n at the end has to be moved inside. Copy and paste. I don't need quarter sizes or half sizes, and that code's going to change too. Okay, so I need to split the node. How do I split it? Well, first I need to find the dimension of largest separation. In the quad tree, we had to find the bounds on x and y. Our KD tree might have more dimensions than just x and y, so we kind of need to calculate our bounds a little bit differently. What I'm going to do here is I want to make this do, let's see, so I need one bounds for every dimension that we have. So I'm going to do something like, I can do this either with a for loop or with a range and a map. I'll go with the for loop as that might be easier to read. So in our neighbor finder, there is a public val called dim, and so I want this to go 0 until dim, yield, and say first we're only going to do, no, let's do this. I'm going to try to make this at least somewhat efficiently. Val, I'll call it min-max. And the idea is that I want this to be a sequence that is as long as the number of dimensions of tuples. And the first value will be the minimum, and the second value will be the maximum. So I'm going to call these x's, even though it's not always going to be x, could be y, z, or whatever else we're calling it. But this is going to pull off one coordinate. So x's equals ps dot map of, I'm going to call this p rocket p sub 0, and then what I want to return from here is x's dot min, x's dot max. Okay. That way I don't have to do this map twice inside of here. And technically I could probably make this a view and improve my efficiency. You'd actually have to do testing to know how much that improves your efficiency and if it's worth putting in there. But we're not going to do that right now. Okay, so this is going to be, it's an index sequence of double-double, where the first element is the min and the second element is the max. And my split dim needs to be the dimension that has the highest separation between those two. Okay, so how are we going to find that? We could do this with a for loop. We can also do it with a folding operation. It is an index sequence, so we can index into it nicely. I'll do it with a var and a for loop, just because I think that is a little bit easier to understand. So we'll say the split dim is equal to 0 for, and I'm going to have another loop here that is d from 0 until dim. This one is not going to yield any value, it's calculating my split dim. I say if the value of min max, and actually do I need the minimum and the maximum values, or do I just care about, let's just do a seps. Separations is xs dot max minus xs dot min. I missed a dot. I might have to come back and change that in just a second. So now this is just the separations in each dimension of how far apart the most distant points are. And so then this is saying, now I'm just picking the maximum value. This would be a little bit easier to do with a fold operation, but I think it's still easiest with the for loop. And the only problem is I'm using a var here, and as you can see in the Eclipse, it's turning it red because that's not ideal. So if, I should spell separations correctly, if separations sub d is greater than separations sub split dim equals d. So I'm just running through and finding the dimension of the largest split. Okay, now what I have to do is interesting. So in order to make a node, this is going to be on split dim and split value. So we found the dimension of the largest split. Now I need to figure out what the value is for these things. In fact, to make this efficient, I'm going to modify my make tree, but I'll do that in the next video. So split value equals, what I really need it to be is I need to call a find median that I pass my points into along with the dimension that I want to find that median on. Okay, because we want to split on the median value. We'll assume we can write a function that does this and does it fairly efficiently. And so we'll come back in the next video and we'll figure out how we can do this, and then how, if we change our arguments up here, we can actually do this even more efficiently than what's in the code right now.